Okay, so we've just previously just covered just an introduction to rills and gullies and rain splash, and we're just going to talk briefly now about how we can link in hydrology, this movement of water through the landscape, to erosion, right? And so hydrology impacts erosion through a whole bunch of interactions and feedbacks. So we have in this little box here, this is how water moves through the landscape. And that's going to be really strongly controlled by the climate and the weather, how the rain falls, how often it falls, and how quickly the soil dries out between rainfall events. Now, these are linked to vegetation. Right? So vegetation is going to impact the rates of infiltration of soil. They're going to impact rates of transpiration, which determine how dry the soil is the next time it rains. And the other interaction is really the interaction with material properties, soil properties. This is going to determine how susceptible a soil is to erosion, but it's also going to determine how much surface runoff is produced. It's going to determine in part how vigorous vegetation can grow or not. And vegetation, of course, feeds back and changes the soil properties, right? Increases hydraulic connectivity. So these erosion and geomorphology and ecohydrology, sometimes a term called ecogeomorphology, looks at a lot of these interactions between these different compartments. So let's recap. A lot of you should have had this already in various aspects of hydrology. But if we think about the hydrology of a hill slope, in the context of a mine site, we have precipitation falling on the hill. Some of that water is going to infiltrate into the soil. Some of that water that infiltrates then will percolate down past the plants and then potentially down to groundwater. In the Australian context, evapotranspiration is going to be a dominant component of the water balance. In fact, more often than not, it's going to be orders of magnitudes larger than surface runoff. Right? So the rainfall that doesn't infiltrate is going to lead to surface runoff. Some of that rainfall that infiltrates will lead to subsurface runoff on hills where we have a confining layer below the surface, or our hydraulic connectivity decreases with depth. And so even though there's not a well-defined confining layer that leads to ponding in the subsurface and saturation in the subsurface, because the hydraulic connectivity typically decreases with depth, we can get subsurface runoff and movement of water below the hills. And sometimes on mine sites this can be a problem because it leads to things called like tunnel erosion, where you get sufficiently high rates of subsurface runoff that you get erosion below the surface. So primarily we're going to be concerned with surface runoff as being the mechanism which causes erosion on hill slopes. But of course all these processes are interrelated. So there's going to be a bunch of direct and indirect processes which impact the amount of erosion that's happening. So you've got a rainfall, okay, as a direct process. It's rainfall is going to impact the soil surface, detach those soil particles and lead to rain splash. Then we have runoff, which is also detaching soil particles and mobilizing them with the flow in sheet, rill and gully erosion, like I mentioned previously. And then finally, we have subsurface runoff leading to tunneling. And all these are direct factors which impact erosion. But of course we have the indirect factors, the other aspects of the hydrology, right? The infiltration rate and infiltration properties of the soil, which lead to the triggering of surface runoff. Then we have the evapotranspiration rate. That determines how dry the soil is and what is the storage capacity really of the soil to absorb that water. Remember, if we have a dry soil, our infiltration rates are going to be much higher initially. So evapotranspiration feeds back and impacts the infiltration rates. Okay, and we're also going to recap some runoff mechanisms. And the two primary, this is surface runoff mechanisms. The two primary mechanisms are saturation excess runoff and infiltration excess runoff. So the saturation excess, when a soil is fully saturated and it just can't take up any more water, then any rainfall falling on that wet soil is going to lead to the generation of overland flow. Right? And typically this occurs at the base of slopes where we might have had rainfall falling on the rest of the hill, over time that rainfall percolates down through towards the groundwater, and then it raises the level of the groundwater. And then when the groundwater rises, or even the perched water table rises up towards the surface, at the bottom of the hill, it's going to be more likely reaching the surface at the bottom of the hill. Then we have a saturated area developing at the bottom of the hill, and then the rainfall falling there will run off and potentially lead to erosion. And it's not necessarily associated with high rainfall intensity events, okay? It can just be, you could have a bunch of rainfall events in the past which have caused the groundwater level to rise, and then any rainfall that falls on that part of the hill will then run off. And the other component is infiltration excess. So we have a high intensity rainfall event which exceeds the capacity of the soil to absorb all that water, which means we have a faster rainfall than we have infiltration. So the infiltration rate is less than the precipitation rate, and then we lead to infiltration excess surface runoff. And this can occur both for wet and dry soils initially. So this should also be a recap for most of you, but typically what we see here is we have the infiltration rate and we have the time. So let's say we started off with a dry soil, in this case here, just above 50 millimeters per hour. We apply a certain rainfall intensity, which is a little bit, say around 50 millimeters per hour. Initially, the infiltration capacity of that soil is much higher, up near 150 mils per hour. As the soil wets up and infiltrates more, the capacity of the soil to infiltrate decreases, because if you remember from module 1, our hydraulic gradient gets longer as the wetting front gets longer and longer. And so the ability of the soil to infiltrate more decreases. And eventually we reach a point where the soil can't infiltrate anymore, and then we get surface runoff being generated, and the infiltration capacity of the soil decreases over time. And beyond this point, we get runoff being generated. So the generation of surface runoff is a combination of both the rainfall intensity and how long the rain has fallen, right? The duration of the rainfall event at that intensity. So these two factors which control the production of surface runoff within a rainfall event. And of course, we may also have to take into account the time between rainfall events, which lead to the generation of surface runoff. So I'm going to leave the basic hydrology there. You should have all had aspects of that in the past. And I'm going to turn now to rainfall factors, but I'm going to concentrate on the aspects of rainfall intensity and not so much the duration, but there'll be bits and pieces of the duration. So rainfall is a risk factor, right? The rainfall in Darwin is going to have a higher erosive potential than the rainfall in Melbourne, right? Darwin actually gets a little bit more rainfall than Melbourne, but the way the rain falls in these big summer thunderstorms over a short period, usually typically late in the afternoon, are going to have a much greater erosive potential than the mizzle and drizzle that you get in Melbourne that just rains the whole year round. And here's an example of this, right? So this is rainfall data that was collected in Germany. And what we've done, the rainfall data was collected at 10-minute intervals. And you can see the rainfall intensity in millimeters per hour collected over about 3 years, a little bit less than 3 years, right? And on the x-axis there is the time. And you can see there's periods where the rainfall intensity gets up as high as 90 millimeters per hour over 10 minutes. Right? It's really quite high intensity rainfall. Some of the other high ones are around, up into the 40 millimeters per hour. Now, if we go up to the next temporal resolution, and what we've done here is we've actually aggregated that rainfall and just looked at hourly rainfall intensity. And when you average the rainfall over the hourly timescale, right, you take 6 measurements and you take the average rainfall intensity over those 6 measurements, you get an hourly intensity. And again, this is in millimeters per hour, but look at the scale here. The scale's dropped right down. So the maximum intensity here, which was up near 90 millimeters per hour, now over that rainfall event over the hour, it's about 17 millimeters per hour. And then if we zoom up to the next resolution, say a daily rainfall intensity, we can see that that rainfall intensity that fell over that day was actually only about 1.1 millimeters per hour over the entire day. Right? So rainfall variability is highly dependent upon the temporal resolution that you're interested in. And so sometimes you'll see erosive indexes of I-30, right? Or I-20 or I-15, which is the rainfall intensity with a certain return period that occurs over a 30-minute duration, because they've decided for some reason that 30 minutes is the relevant timescale that they're interested in for their erosion study. Now, we can actually look at the statistics of rainfall, right? How boring is that, huh? But we can, for example, and people have done that, and we can generate models which reproduce this rainfall variability. And so here's an example of a model that reproduces observed rainfall variability. And I actually used this as part of my PhD thesis. So we started off with, say, a rainfall intensity of about 18.75 mils an hour. That's pretty accurate, right? But that 18.75 mils was spread over 96 minutes. Now, if we disaggregate that rainfall, we break the rainfall up into 48-minute chunks. There's a bunch of rules which tell us how the variability changes as we move from the 96-minute resolution down to the 48-minute resolution. And those same rules turn out to be consistent if we move from 48 to 24 minutes, or from 24 down to 12 minutes, and so on, right? 24 down to 12, and then 12 down to 6. And it turns out that the variability we can describe in terms of this power law. There's a power law relationship between the temporal resolution that we're interested in and the temporal resolution that we started at, say, or our lowest temporal resolution, say 6 minutes. And that's related to this exponent b, and these parameters are actually parameters of a probability distribution, a binomial distribution, which describes this ratio of the amount of rainfall that fell at this time, the amount of rainfall that falls at this time. So the take-home message: rainfall variability increases as we decrease our timescale. And what I did, I looked at how we could use an infiltration equation to describe how runoff was generated on some soils as affected by this rainfall variability. So sometimes you'll see what's called Huff curves, and these Huff curves describe the proportion of rainfall here. This is H over H at a certain time over the total H. So this is the proportion of rainfall that's fallen during the event, right? So this is, number one is all the rainfall has fallen, and 0.5 means that half the rainfall for the event has fallen. And on this axis here, we have the time of the rainfall event, right? So this is the beginning of the rainfall event, this is halfway through the rainfall event, and this is at the end of the rainfall event. And these Huff's curves were generated for 100,000 different rainfall events, but all those rainfall events had a 96-minute duration, and they all had the same 18.75 mils per hour average intensity, spread over that 96 minutes. So what we can see is that some of those rainfall events here, particularly these events here, had rainfall that fell very quickly. More than 60% of the rainfall fell in the first 25% of the rainfall event, and then the rest of the rain fell in the rest of the event. And you can see that the average rainfall intensity is fairly constant, right? When you look at all the rainfall events in total. Now let's have a look at the discharge, the runoff that's occurred as a result of these rainfall events, right? This is like a a sample of all the possible rainfall events that happened. And down here we have the QP on H. So this is the proportion of surface runoff that was produced of that rainfall event, right? So 40%, the 0.4 here means that 40% of the rainfall became runoff, whereas 0.1 means that only 10% of that rainfall event became runoff. Again, on this axis we have the duration of the rainfall event, beginning of the rainfall event, end of the rainfall event. And we can see that 50% of the rainfall events by the end produced 30% of runoff for this rainfall, right? For this this soil that was tested, and for this duration of rainfall event and this average intensity. Okay, so it's just a modelling exercise to look at the impact of rainfall variability. We can also see that let's see. So we have here, this is a 99 or 1 percentile. So this is the 1 percentile of runoff events. We can see that 1% of the events didn't produce any runoff, right? Almost no runoff until about 60% of the way through the storm. And then the runoff gradually increased thereafter. Whereas another 1% of the events had produced 40% or almost 40% of the runoff by about 45% of the way through the event. And that's because we have these thresholds for runoff being generated, right? So these events probably had very high rainfall intensities. The 1 percentiles over on the left-hand side there had probably very high rainfall intensities initially to get the runoff being produced. Whereas these events probably had very low rainfall intensity initially and then high rainfall intensity towards the end of the event. We can actually go and look at what types of rainfall events then caused the different types of runoff. So here we have example 2 soils, a silt loam and a sandy clay, which we tested in the model. And here we have this line here gives you the mean rainfall intensity, right, for all the events sampled, and you can see that's just the line through the middle. And that 1 means that fell at basically the rainfall intensity that we prescribed, the average rainfall intensity for the event. So numbers below this means, below 1 means that the rainfall intensity is less than average. Above the line means it's more than average. Okay. And what we have here, we have the events which produced the lowest 25% of runoff here in Q1. And we have here the rainfall events that produced the largest 25% of runoff. And here we have the rainfall events that produced the middle 25%, the lower 25 to 50%, and then the 50 to 75% as the stars there. So we can see the rainfall events here for this silt loam that produced the largest amount of runoff, the little black triangles. They started off with low intensity. The intensity built throughout the event and then peaked towards the end of the rainfall event. And the rainfall events that produced the least amount, the open diamonds, started off with a high rainfall intensity. The rainfall intensity decreased throughout the event and then continued to decrease all the way to the end. And the other rainfalls were somewhere in between. And we can see here similar sort of thing for this sandy clay loam, except the pattern of rainfall was slightly different. So the rainfalls that produced the greatest runoff, the dark triangles here, again started off low, then they gradually stepped up. And then there was a sudden increase in rainfall intensity that sort of plateaued towards the end of the event. Right, so these patterns of rainfall that are emerging that produce lots of surface runoff are strongly dependent on the type of soil that you have. And you can see that you can get a large variation in the rainfall patterns that produce different types of runoff. Okay. But potentially you can classify rainfall events by how the rain fell rather than just by lumping it across a whole event as been done in the past. Okay, so let's return to rain splash, which we covered in the previous lecture. Right. So when we have a raindrop falling, right? Raindrops often fall from the clouds. They have a certain size after they've fallen out of the cloud where all the humidity is. And the friction of the air causes them to stop accelerating, right? So the friction force is opposing their downward movement to the point where they no longer accelerate anymore. So they've reached some sort of terminal velocity. Okay? They're still falling, but they're no longer accelerating due to gravity. Right? And so we have here a terminal velocity on the y-axis, and we have here a drop diameter. So you can see that the terminal velocity increases fairly rapidly with drop diameter and then it begins to plateau again, right? And this is probably, it's beginning to plateau because the drop is starting to spread out and either break apart and form smaller droplets, or it's just spreading out and forming a bit of a plate instead of a nice little round droplet. And that plate increases the friction and reduces the terminal velocity. So the energy that's associated with that droplet we can describe by its kinetic energy. This is the energy associated with its velocity, its movement. And that kinetic energy we can calculate by saying it's half times the droplet's mass times its velocity squared, right? And the force associated with that droplet, or its momentum, m, is given by its mass times its velocity. Okay? So what you can see here is the larger the mass of the droplet, the larger its force it will have when it impacts the soil, or it's larger its kinetic energy, right? And also, the larger the droplet, the larger its velocity is going to be. So we have a double whammy here. Because large drops can fall faster, and they have a larger mass, they're going to have much greater momentum than smaller droplets. And so this is a curve that was produced out of the USDA, which describes how to relate the rainfall intensity, in this case in the US units of inches per hour, you can see some conversions down here, into the amount of energy that's applied by that rainfall intensity onto a soil surface, right, in terms of its kinetic energy. Right? So this is a rough estimate of what the kinetic energy applied to a soil is. And so you can see down here, we can convert this unit energy into megajoules per hectare per millimetre of rainfall that's fallen on the soil surface. Hello? Sorry, I get these spam phone calls. I don't know how to get rid of them. Right. So as the rainfall intensity increases from 0 to 1, then we get an increase in the total amount of energy that's impacting onto a field, for example. But then it starts to plateau, right? And we get averaging out and all sorts of things going on. And we don't get a significant increase in the energy that's being impacted on the soil surface. This is inches per hour, right? So an inch is about 2.5 centimetres. So that's a significant rainfall intensity that we're looking at here, right? And part of the reason for that, part of the reason it plateaus here is because we're starting to get ponding on the surface and we're getting water that won't infiltrate. And so that water is buffering raindrop impact on the soil surface and not letting it actually impact soil particles as strongly. Now you can actually measure raindrop size, right? So there's a whole bunch of different types of equipment that can do it, and one of those bits of equipment is called a disdrometer. Some of them have lasers, some of them use acoustics, a whole bunch of different ways you can measure it. But you can actually measure raindrop size, and people have done this for a whole bunch of different storm events. And so what you can see here is storm events of 0 to 1.3 mils per hour, all the way up to rainfall events that had over 265 millimetres per hour, right? That's a massive storm. But you can see a clear trend, right? A clear pattern. These are like histograms of the raindrop size. This is a percent total volume on the left-hand side versus the raindrop diameter in millimetres. So for low intensity events, we have small raindrop sizes typically dominating, with very few larger raindrops. But as the rainfall intensity increases, we go from 1.5 through to 10 to 12 millimeters all the way up to, say, 76 millimeters per hour. You can see there's a shift in the raindrop size towards larger and larger raindrops. And then for this particularly intense, probably cyclonic event, we have a peak here, concentration of really large droplets above 4 millimeters in diameter. And again, these guys, Carter et al., they developed their kinetic energy versus their rainfall intensity relationship based on all these raindrop sizes that fell throughout particular events at certain rainfall intensities. So rainfall is an important factor to consider when you're thinking about erosion, and it's going to change from place to place and region to region. So in the universal soil loss equation, which I'm going to cover later on briefly, they have rainfall factors that you can put in which account for some of these differences in the rainfall intensity and the raindrop sizes. So rain droplets have momentum and kinetic energy. The rainfall kinetic energy relates to the total number of raindrops at a given intensity. And rainfall intensities of 50 to 100 millimeters per hour, we can even see that for smaller events actually, have a greater number of large droplets. Right? We get a general shift in the droplet size as the rainfall intensity increases. So the higher the impact velocity, the greater the amount of soil splash erosion that we have. As we said in the previous lecture, 2/3 of that raindrop energy then expended to form impact craters and the little mounds associated with it, and the remaining energy goes into forming spray where the soil particles are injected into the air and deposited a fair distance away from where the raindrop happened. When the rainfall intensity is high enough, when we get ponding on the surface, we have thin films of water actually near the soil surface that can actually increase the effect of droplet impact. But when those films of water become larger again, then they're going to buffer the raindrop impact and reduce the amount of soil erosion and raindrop impact. And as I said before, fine sanding material is going to be most affected because it doesn't have any significant interparticle bonding.